Okay, so suppose we have a source, AC source, it has some impedance in series. Okay, suppose that is R, call that R naught. It may also have some reactive part, call that Jx naught. Okay, and these are fixed values. This is fixed, constant. This is also fixed, constant. Okay, and the source voltage is also constant, fixed. Now here we connect a load, suppose which is R plus J X. This is the load. Now these two may vary. I can change these two. Now the question is, under what condition the power consumed by this load, okay, so this is the load, under what condition load power will be maximum? For R equal to how much and X equal to how much, load power will be maximum. What is the expression of load power in this case? If say this voltage is V, how much will be the load power? Can I write it as V divided by R naught plus little r plus J X naught plus little x? Okay, so this is basically the current I.
Correct.
Okay, yeah. Now if I take the square of the magnitude of this current and multiply by R, I get the load power. Okay, so if suppose if this V is V angle 0 degree, okay, so then this will be V square by V square into R above, and what will be the denominator? Correct? Okay. Now, when will this quantity be maximum? So one thing we can do, we can differentiate this quantity as functions of with respect to little r and little x and equate them to 0 to get the condition for maximum power. Okay. Kindly mute yourselves.
Sir,
Yeah, yeah.
sir, when x is equal to minus x naught and small r is equal to r naught.
Yes, right. You are absolutely right. So we don't need to differentiate. Okay. So I mean, you can see that for any given value of little r, okay, for maximum power, maximum load power, little x should be equal to minus of capital X naught. Okay, because then this term will be 0, denominator will be minimum, power will be maximum. Okay, acha. Then similarly, for any given value of x, for maximum load power, how much should be the little r? To find out that, yeah,
0.
0, no, because little r is
Okay.
also there in the
Yes, yes.
yeah. Okay, so you may now do a derivative, okay, but let me do it in your style, which you taught me in an earlier class. Okay, so let me write it this way. Let me divide the okay, before that let me just expand it. V square by R, R r naught square plus r square plus x naught square plus let me write it this way, x naught square plus x square plus 2r naught r, correct? Okay, now if I divide with little r both the numerator and the denominator, so let me divide here as well as so here we will have root r whole square, okay, and here this will become r, here let me write root r whole square, okay, and this is like this. Am I correct? Please check.
I think it was correct, sir.
Yeah, still let me do one more. R naught square plus x naught plus x whole square divided by r plus 2r naught plus r. Okay, now this is equal to v square divided by r naught square plus x naught plus x whole square by root r minus root r whole square. Okay, so we will get the first term, then this term. Now we need 2r naught plus, I need space, uh, 2 into root r naught square plus x naught plus x whole square minus sorry divided by yeah, that's the step. Okay, so now for maximum power we can make this term equal to 0, which implies that r little r should be root over r square plus x naught plus x whole square. So which is basically same as the magnitude of the I mean other series impedances, total impedance in series. Okay, so here therefore the conclusion is r should be equal to root over r naught square plus x naught plus x whole square. Now combining these two facts, number 1 and number 2, okay, so number 1 says that for any given value of little r, x should be equal to capital X naught minus capital X naught, and for any fixed value of little x, r should be this. Now if both little r and x both are variable, then what happens? Then what should be the best criteria for maximum power?
R will be R naught and X will be minus X naught.
Then maximum power occurs when x equal to minus x naught and r equal little r equal to r naught. Now if little x is 0 constant, then what should be the value of little r? Then little r should be
root over r square
Root
not a
over
square
r
plus f
plus
not a square.
plus x naught square.
Yes, absolutely right. Okay, so let us take an example problem. Okay, so here we have a given circuit. This resistance RL is the load resistance variable. We have to find the value of this load resistance for which maximum load power will be obtained. How do we solve this? Okay, so consider this part of the circuit together. Okay, what to do first? Let us first find the Thevenin equivalent of this part. What will be the Thevenin equivalent? Some voltage source together with some impedance. Okay, call that ZTH. How much is ZTH? Before that, how much is the impedance of this inductor? Okay, 4 millihenry, omega is 1 kiloradian per second. So XL will be J4 ohm.
4j
Yes. How much will be XC?
minus 2j
Minus J2. Absolutely right. Okay, so then how much is the, if I call this node A and node B, how much is the Thevenin impedance between node A and node B?
2 root 2.
Right. So ZTH will be, basically we have two parallel paths. No, not 2 root 2. Two parallel paths are there. One is 2 ohm. And how much is this path? J2. Together in parallel. This is in ohm. Okay. So how much is this? 2 into J2 divided by 2 plus J2. So Z Thevenin will be, or let me just find the magnitude of Z Thevenin. How much is that?
Root 2.
Yeah, root 2 ohm. So what should be the value of RL? It should be root 2 ohm. Okay. Fine. Next, let us take one more example. Okay, so we have a circuit which has two parts. Circuit A one part and circuit B another part. Okay, and here there is a resistance R. We have to find the value of R so that the power going from circuit A to circuit B is maximum. Okay, the power from circuit A to B should be maximum. How do we find? How do we do this? Okay, so first let me write this voltage as, this is 10 angle 0 degree. Okay, in volt. Then suppose this current is I, suppose I ampere phasor, and suppose this voltage from here to here is V plus minus. Okay, then required the power that we are considering is how much? Is V I star real part of that, and we have to maximize this. Okay. Achha, now suppose if I consider this point as the reference point, 0 volt, then this point is at 10 volt. What else can we say in this circuit? This point is at 3 volt.
3 volt.
Then how much is I bar? That is 10 minus 3 by R plus 2. If this R is in ohm. Okay, then how much is, so this is basically a real number, okay, because angle is 0 degree. Then how much is V bar? V bar will be 10 minus 2I, correct, which is 10 minus 2 into, so this is 7 by R plus 2, so 2 into 7 by R plus 2, okay, so this is in volt, this is equal to 10 R plus 20 minus 14 is 6 by R plus 2. Am I correct? So then power will be just this product of this current and voltage, 7 by R plus 2 into 10 R plus 6 by R plus 2. So let me write R plus 2 square. Okay, which is equal to, I can take 2 common, 14 into 5R plus 3 by R plus 2 whole square. Now when will be this power maximum? When the derivative of this quantity with respect to R will be 0. Okay, so if I call this P, then dP dR should be equal to 0. So 14 is a constant. Okay, so let me differentiate it. So we will get 5 into R plus 2 whole square minus 2 R plus 2 into 5 R plus 3 divided by R plus 2 whole square. This should be equal to 0. So from this 1 R, what do we get? 5 R plus 2 minus 2 5 R plus 3 equal to 0. From this you can find what is the value of R. How much is that? We have 5R minus 10R, so minus 5R plus 10 minus 6, so that means plus 4 equal to 0. That means R should be 4 by 5, that means 0.8. Okay. Any questions so far?
Sir,
Yes.
means 3 volt, 3 volt is there, right, sir? Like if I take like 3 volt is a series with a zero resistance,
Right, right.
then I can write, then I can zero resistance and minus J resistance are parallel, so it will be all 3 volt resistance.
Yes, yes, you're right.
So
I mean, basically this
then it will be like,
yeah, I mean, basically this is equivalent to just this source. This will not, I mean, this is effectively not there. You are right. If you
yes,
calculate the
means
Thevenin. Yes.
if I do like 10 minus 3, like total voltage is 7, right?
Mm-hmm. Yeah.
Then
So you are
total voltage
basically.
is 7, sir.
Hmm.
Then we did similar case before, like when you said like R should be 0 because R is with series with 2. Here, how come like R is 0.8? I could not understand.
No, you. I mean, you see here what we have done. I mean, we have done in detail, na. So you are comparing this with some earlier problem, maybe. Okay. So then we have to go back and see what was that earlier problem. What's the difference? Okay. Yeah. So I mean, the setup might have been different. I
Sir,
don't remember. Yeah. Yeah.
sir, if we do like total voltage is 7, right, sir?
Yeah. So, okay. So let me. So you are saying that this circuit is equivalent to uh, uh, 7 volt. Uh, I mean this side's plus minus 7 volt AC. Uh, 2 ohm and R. Okay. Then
Yes.
what? I mean, we should not actually even come to this step, because if we are doing, if you are coming to this step, then we are merging circuit A and circuit B together. Okay, but we want to find the power which is going from circuit A to circuit B. If we merge circuit A and circuit B together, then we cannot tell any longer, I mean, what is going from part A to part B, because they are already merged.
Okay.
Okay.
We should find maximum power in the circuit B itself. Trans.
Pardon?
Okay, sir. I found like total. Okay, okay. My mistake.
Okay, fine. Yeah, if you got it, then it's fine. Okay. Fine. So now let me talk about another thing, something uh, new, which is called resonance. You know, if we have an inductor, the impedance, if the inductance is L, then the impedance is j omega L, and if we have a capacitor, capacitance C, then the impedance is j by omega C, minus j by omega C, and you see both are imaginary, but one positive, another negative. So therefore, it is possible that if we connect them in series, one positive, another negative, they may cancel each other. Okay, so they may cancel each other. So it may happen that j omega L minus j by omega C is equal to 0. When will that happen? That will happen, I mean, if omega L is equal to 1 by omega C, that means, or omega equal to 1 by root LC, if the frequency of the supply, the inductance and the capacitance are related by this equation, then overall this series combination will behave like a short circuit. Okay, so will act like a short circuit. Okay, this is called this. I mean, this phenomena is called a resonance. Okay, this is called a series resonance because the inductor and the capacitor are connected in series. Again, if you now connect these two in parallel, and let us see what happens. This is j omega L, this is minus j by omega C. How much is the equivalent impedance? JD cube. That will be product of the two divided by the sum of the two, and again the denominator can cancel, the two terms in the denominator can cancel each other and make the denominator 0. So it is possible that this will be equal to, will tend to infinite, okay, if say again omega L is equal to 1 by omega C, that means again omega is equal to 1 by root LC. So then these two together will behave like an open circuit. Okay, this phenomena is called again a resonance, but this is called parallel resonance. Okay, yeah. One more thing you notice here, suppose if I call this current as IL and this current as IC, and suppose the voltage is V from here to here, from left to right side, okay, and if this current is I outside, so this is also I here, then how much is I? So it will be sum of IL plus IC, the two currents, but now IL is V by j omega L and this is V by 1 by j omega C. This will become equal to 0 if omega L and 1 by omega C are equal. That means so what happens now? If I call these two nodes A and B, now no matter how much voltage you apply between A and B, the current going from A to B is always 0 under this particular condition. Okay, that means no matter however voltage you apply, no current is flowing, so impedance is infinite, very large. So it's like an open circuit, no current can flow. Okay, so this is called the parallel resonance situation. Now, for under this situation, so suppose we consider we have a source and say we connect a resistance, an inductor and a capacitor all in series. Okay, inductance L, capacitance C, resistance R. So these are all constants, constant. Okay, but say the source is variable. Suppose the source voltage V RMS is constant, but the frequency, that means or omega, they are variable. Okay, so this is a variable source whose RMS value is constant, but frequency or angular frequency is variable. Okay, now in this circuit, if I say connect an ammeter and then I do the following, I change the frequency and note the value of this current I using this ammeter for different frequencies, and then I plot a graph. Okay, so let me plot a graph. Frequency omega x-axis and the current in the y-axis. Okay, so I mean the magnitude of current. Okay, so how will this graph look like? When will this current be maximum? if I write this
There
as,
is
Omega naught at
Yeah.
the
very low.
resonant frequency.
right. So basically I, magnitude of I is equal to VRMS divided by R plus j omega L, uh, j of omega L minus 1 by omega C. Okay, magnitude of this. When will this current be maximum? When omega L is equal to omega C. So suppose that point is somewhere here. So suppose this is the frequency corresponding to 1 over root LC. Then here the current will be maximum. How much will be the maximum current? How much will be this value? When
VRMS upon
so
R.
it will be VRMS by R. Now if I change the frequency, suppose if I increase the frequency, then what will happen to the current? The current will decrease.
Decrease.
Okay, why will it decrease and how long will it decrease? What happens if I
Tending
take,
to zero.
yeah, so if I take a very large frequency, yeah, if I take a very large frequency, then what happens? Then this inductor impedance, this j omega L, will be very large, and 1 by j omega C will be 0, but overall the denominator will be very large, so it will come down to 0 gradually. Okay, and what happens at a very low frequency, say at omega equal to 0? The inductor will behave like a short circuit, because omega 0, so j omega L, this will be 0, but what will happen to j minus j by omega C? Here the denominator
Very,
is
very large
0.
value.
Yeah, so this will be infinite. So again the current will be, so that's how this graph will look like. Okay, then yeah, now suppose I take another circuit where I have, say, a resistance. Okay, or let me put everything in parallel. Resistance, inductor, this is R, this is L, this is C. Okay, and here I put an ammeter to measure the current. Now again the voltage source has a fixed RMS value, constant value, but variable frequency. Okay, now this current is I, and again I plot a graph of current, magnitude of current, as a function of the frequency omega. So how will this graph look like? What do you think? Okay, so at the particular frequency omega equal to 1 by root LC, then what happens? Here we have j omega L, here we have minus j by omega C. They are in parallel. So here overall the current will be 0. So how much will be the total current I? It will be VRMS by R, maybe somewhere here. Now if I say increase the frequency, what happens? If I take a very large frequency, then what happens? This capacitor impedance at a very large frequency will go towards 0. The capacitor will act like a short circuit at a very high frequency. So therefore, the capacitor will allow a very large amount of current. So we will have a very large amount of current at a very large frequency. Okay, And then what happens if we have a very low frequency, say 0 frequency? At 0 frequency, this j omega L will be 0. So this inductor will allow infinite current. Okay, so again at a very low frequency, current will be very high. So the graph of this will therefore look like this. Okay, so increasing in both the directions. This is the minimum point corresponding to omega equal to 1 by root LC. Okay, so yeah. Now let us do one more thing. Let us draw phasor diagram expressing the voltages and currents. Okay, so suppose we have this circuit, we want to draw a phasor diagram representing the voltages and currents. Okay, so let me call this voltage V bar plus minus from here to here. Okay, then how do we draw the phasor diagram? So suppose the current I is here. I mean, we don't know the value or the angle of this current I. So suppose it's here, okay, or maybe let me draw with an arbitrary angle. Suppose this is the current I. Okay, then suppose this voltage across the resistance is VR plus minus, then VL plus minus, and VC plus minus. Okay, from yeah. Now, how will this vector VR be? This phasor VR be? Yeah. So VR is basically I into R. So it will be somewhere here in the same direction, VR. Okay, which is equal to I into R. Yeah, any question? Okay, then how will be this phasor VL? VL is I multiplied by j omega L.
Omega C.
Yeah, so it will be, yeah, any question?
Perpendicular of
Absolutely right. So it will be somewhere here. So this will be VL, this angle will be 90 degree. Okay, and how will be VC? That is I by j omega C. So that will be 90 degree in the opposite direction. This is VC. Now, depending on the frequency, the length of VL and VC, they may change. If I increase frequency, then VL will increase, but VC will decrease. But if I now decrease the frequency, okay, then VC will increase and VL will decrease. So it may happen that at a particular frequency value, VL and VC will be exactly equal and opposite to each other. Okay, then the resultant voltage will be how much? Then the resultant voltage will be just equal to VR. So if this is, let me call it Vs, so then Vs will be that equal to VR. But if for any other frequency, suppose Vc is smaller, if Vc is here, Then when we add VL and VC, okay, so the it will be long, I mean upper side is longer, so it will be somewhere here, I guess, plus VR. So this will be the resultant voltage, VS, source voltage. Now, another thing I want to say. Okay, so this is the phasor diagram representing the relation between voltages and currents in this circuit. Okay, now let me copy this and okay, if I say rotate this diagram, can I do that? Does this also represent a phasor diagram for this circuit? Or if
Yes.
I rotate it further, is it still valid? Or if I say make it like this, is it still valid? And if it is valid, why? Can anyone tell?
Sir, because
Yes, go ahead.
because the relative position of I vector, VR vector, so they are not changing. The relative position of each vector with
Absolutely
respect
right.
to each other.
Yeah, so this is only showing the relative position with respect to each other, among the voltages and currents. Absolutely right. Okay, there is another way of explaining this. This is an important insight about the phasor diagrams. So we have solved a lot of questions, numerical problems, and we saw that dealing with AC circuits using phasor representation is very similar to DC circuits. But you may ask this question, what does this phasor mean at all? What is the meaning? Okay, so one interpretation of this may be like this. Okay, so I mean, suppose we have any voltage or current which is in general of this form, A sine omega t plus phi. This is the functional form. Okay, now we said a shortcut way or a shorthand notation of representing this is just to write the number A by root 2 and the angle phi as a complex number, because this function has essentially two variables, two parameters, A and phi. This complex number also has two parameters. So this you can think a shorthand notation or a shorthand secret code to represent or encrypt this function as a number. However, we can also elaborate this a little more. So what are we doing to get the functional form into a phasor form? First, what we are doing is this. We are first replacing, so replace sine function with exponential e to the power j something. Okay, so we originally have A sine omega t plus phi, and then after the replacement we get A e to the power j omega t plus phi. Okay, after this what we are doing? We are putting t equal to 0, put t equal to 0. Okay, if we put t equal to 0, we get A e to the power j theta, j phi. Okay, and then finally divide by root 2. So we will get the final phasor. Now let us again look at the functional form. So a sine omega t plus phi, what does it represent? It represents a function like this, which sinusoidally varies with time, okay, starting from the angle phi. But what does this function a to the power j omega t plus phi represent? This is a complex function, so to draw this I need a three-dimensional space. So let me draw in this way. Okay. Suppose this is the time axis, and perpendicular to that, perpendicular to board, we have the complex plane. This is real axis, this is imaginary axis. Then how will this graph or this function a to the power j omega t phi look like? Any idea? It will basically as time changes, this function basically rotates on the complex plane. Okay, so yeah, so it will be it will be like a
the helix.
Yes, helix you can say, or a spiral you can say, like this. Okay, so now what's the relation between this spiral and the original function? The original function is just the vertical projection of the spiral. Okay, now this is a one-to-one mapping, one-to-one and invertible mapping between this real sinusoidal function and this complex helical function. Given the sinusoid, you can always find this helix that we are talking about, and given the helix, you can always get back which original sinusoidal function we are talking about by taking the vertical projection. Okay, just vertical projection. And then here we are putting t equal to 0 in the second step. So putting t equal to 0 means we are just considering the starting value. Okay, so if I just draw the complex plane, real axis, imaginary axis, then this line, suppose this angle was phi at time 0. Okay, so here we are just representing the starting value. This is phi, this length is a. Okay, and then finally we are just scaling it, we are just resizing. So resizing is not very insightful, it's just a scaling, resize or scaling. But before that, in the second last step, we are just drawing one line, one vector or one phasor to represent the original function. But how do we get the original function from this one line? What is the rule? What is the prescription? The rule is that we have to rotate this line in the complex plane, okay, at an angular frequency of omega. Okay, so rotate counterclockwise at omega frequency and take projection and project. Okay, so if we do that, so if we rotate this line and take projection at different time instants, we will get the original function. Okay, so now with after this discussion, if I just go back to the phasor diagram we draw earlier, okay, so here in this phasor diagram we have a current, we have a few voltages. These lines are representing just the initial values or initial vectors which we have to rotate counterclockwise to get the original and to project to get the original function. So here if I just rotate this diagram, okay, okay, suppose this is time t equal to 0, okay, and if I project this current on the vertical axis, I'm getting say 0, so current may be 0 at time t equal to 0. Then if I rotate it after some time, okay, the current comes here. Now the vertical projection is positive, so current will be, so now if you look at the current, so now the current is positive. We can rotate it further and further, and at each and every time instant, if we project these lines on the vertical axis, we will get the value of the currents and voltages at that moment. So basically, rotating means changing the time. If this is the phasor diagram at one particular time, if I rotate it, this is the phasor diagram at another particular time. Okay? You can also say that, okay, I will change, I will reset my clock. Maybe I will advance my clock by some time or delay my clock by some time. Okay, so then the new diagram will just get rotated. Okay, so that's the overall picture or overall understanding about the phasor diagram which I want to convey. Is it okay? Is it fine?
Yes, sir.
Okay, fine. Thank you. Achha. Now, yeah. So in the rest of this class, I will talk about measuring instruments or equipments, voltmeter, ammeters, wattmeters, etc. Okay. So voltmeter, say an ammeter. Ammeter has this symbol which has two terminals. This is called ammeter. You know, this is used for measuring current, measures current. The symbol of a voltmeter may be like this, V inside a circle, so voltmeter to measure voltage. Okay, so we will also talk about wattmeter to measure power. Now, first of all, suppose if we have a source and then there is a load, then some current is flowing. Suppose this current is I. I want to find out how much is I. How to find it out? Okay, so to find I, we have to put the ammeter here. Okay, so ammeters are okay. So this is so ammeters are to be connected in series with the line where we want to measure current. Okay, I guess you have studied this in schools. Now, if I want to also measure the voltage, okay, across this load, say how much is this voltage from here to here, what do I need to do? We have to put a voltmeter between these two terminals. Okay, so voltmeters are connected in parallel. between the points, between the nodes whose potential difference we want to measure. Potential difference is to be measured. Now, there are two types of meters, okay, that we will talk about. Number one, direction insensitive. Let me call direction sensitive first. Direction sensitive, and number two, direction insensitive. Okay, so if let me copy this. Okay, so for a direction sensitive ammeter, it will have the two terminals must have a plus minus marking, where this plus minus marking means the ammeter will give positive reading if current is flowing from plus to minus direction, and it will give negative reading if it is flowing in the opposite direction. Okay, so positive reading if current flowing from plus to minus. Okay, and for a voltmeter, if we have a voltmeter here, this can also be direction sensitive, so it will also have two terminals marked as plus and minus. Okay, so for voltmeters, so positive reading, so here I was talking about ammeters. Ammeters provide positive reading if current is flowing from plus to minus, and for voltmeters provide positive reading if plus terminal is at higher voltage, plus terminal is at higher voltage, higher potential compared to the minus terminal. Okay, now so normally this is very useful for DC circuits. Okay, so this is useful for DC circuits. Now, if I consider an AC circuit, okay, then what will happen to the reading of these two meters if we use a direction sensitive meter? The voltage and current, they are changing with time, so that means the reading of the meters should also change with time, and it should keep changing, plus minus plus minus plus minus. But suppose if I have a 50 hertz supply, so that means the reading should change between plus and minus 50 times as every second. Okay, so normally meters cannot change its reading so fast. So what will it give as its reading? It will give average. Yes, absolutely. Okay, so basically then I mean these meters, this type of meter, this type of meters provide average reading, provide average value. So in case of a sinusoidal AC, the reading will be 0. So we cannot use these meters. because no matter how large the voltage and current is, the reading is always 0. So therefore there is another type of meter which is not direction sensitive. Okay, those are basically RMS meters, because they measure RMS value of a voltage or current. Okay, so they measure RMS value, and therefore RMS value is always positive irrespective of the direction of the current, in which direction the current is flowing, and irrespective of the voltage. Okay, so this is useful for AC circuits, more use. Yeah, this you can also use for DC circuits, useful for both AC and DC circuit. But if you use this in DC circuit, you will not be able to decipher the direction of the voltage and current. Irrespective of the voltage and current direction, it will always give the same reading, okay, because it reads the RMS value. Okay, and in a circuit diagram, we will not see the plus minus symbols beside these voltmeters and ammeters if the meter is an RMS meter. Now one more thing. Okay, so we now tell me how much should be the internal resistance or impedance of this ammeter. Internal impedance,
0.
absolutely.
Ideally
0, practically as low as possible. Okay, internal impedance of ammeter should be ideally 0. So in this course, we will assume it to be 0. Okay, practically it is very small. Why is it so? Why do we need this to be 0? What will happen if it is not 0?
So since we require the exact value of
Because
the
it will not show the true current.
Yeah, so because suppose I had this circuit originally and I wanted to measure the current. Okay, suppose this is Z, this is V. Okay, now so I was equal to V by Z. Now if I insert the ammeter, and if the ammeter also has some impedance, if it call that ZA, then this current will change. Then this current will become V by Z plus ZA. So the current value will change. So it will not change only if ZA equal to 0. Okay. So therefore, so that we get, so that the ammeters do not change the original circuit, we need the internal resistance or impedance to be as low as possible. Yeah, please mute yourself, Bomidi. Yeah, please mute yourself. Okay. Now similarly, internal impedance of any voltmeter, how much should it be? Should be as large as possible. In this course, we shall consider it to be infinite. Why is that so? Once again, I mean, when say here we are connecting this voltmeter, okay, so when this voltmeter was not there, the current was flowing only through this load. Okay, now as soon as we connect this voltmeter, some more current can also flow through this voltmeter. Therefore, the original circuit is changing. Okay, so original voltage will also change. So that it doesn't happen, therefore we need the voltmeter impedance to be infinite so that no current can flow through it. Now let us talk about wattmeters. Okay, so what does it measure? It measures power, and power is nothing but a voltage and current multiplied together. Okay. Now, therefore, an wattmeter you can think is a combination, some sort of combination of a voltmeter and an ammeter. Okay. So, an wattmeter basically has two coils inside. One is called the current coil, another is called the pressure coil. Okay, so current CC for current coil, this is for measuring current, and PC for pressure coil, you can also call it potential coil, this is for measuring of voltage. Okay, and both the coils are direction sensitive, so we should put plus minus and plus minus to indicate the direction. Okay. Now, the current coil measures current, so therefore, this is similar to ammeter, and pressure coil is similar to a voltmeter. Okay. What do I mean by that? Internal impedance of CC should be how much, and internal impedance of pressure coil should be, so current coil should have 0 impedance, pressure coil should have infinite impedance. Practically as small as possible impedance for current coil and as large as possible impedance for pressure coil. Now, suppose if I have a circuit, some source, and then some load, current is flowing, we also have a voltage difference across the load. Okay. Now the question is how much power is consumed by this load and how do we measure this? How to measure load power? How to connect an wattmeter? This is the last thing we are doing today, how to measure load power. Okay, so load power is basically what? The product of load voltage and load current. Yeah, I also have to mention the direction of voltage and current I am talking about, otherwise it's incomplete. So I am talking about the voltage with this sense, plus above, minus below, and current from top to bottom. Okay, then load power, or better to say power consumed by load, power, electrical power consumed by load is equal to V into I, this voltage and this current. Okay, this may be time varying, so let me write IT and VT. Okay, VT and IT. Okay, and we have to multiply these two in this particular direction, in this sense. Okay, so now here I take an wattmeter which has two coils, current coil CC and pressure coil. Very high impedance for pressure coil, that's why we are showing so many turns, and current coil has low impedance, so we are showing less number of turns. Okay, so CC and PC. Okay, suppose this is plus minus, how do we connect it? The current coil should measure IT. Okay, so for that let me break this circuit here and put it in this way. Now the current coil is measuring IT in which direction? From plus to minus, that means from top to bottom of the load. Okay, now how should I connect this pressure coil to measure this voltage? I want to measure the voltage of upper side with respect to lower side. So therefore, let me connect the minus terminal below and plus terminal. How do I connect? You may connect like this. Okay, so that's how to connect an wattmeter. Yeah. Now, one more thing I would like to say here. Yeah, now this current IT and VT, they may vary with time. Okay, so the wattmeter will multiply this current and this voltage at each and every moment of time and then take an average over time. Okay, so wattmeter will multiply IT and VT and calculate the time average of this product IT times VT. How does it multiply? How does it calculate the average? That physics we are not going to discuss in this course, but the function is like this: multiply and take average, multiply and take average. That's the function of an wattmeter. Now, the other thing I wanted to say here is that, okay, so in this circuit, if I just remove this connection from here and instead if I join it just here, will the wattmeter reading be different? Is there any difference here? If so, what is the difference? If not, why not? Any suggestion?
Sir, I think it will be different because
All difference
It
which
will
is
different.
because CC is also attached with the load.
Yeah, so your observation
Very
is
low
very
impedance.
correct. Your observation is very correct. Now, so the potential difference across CC will also get added to the potential difference across the load, right? That's what are you saying? Okay. Now, so if so, now tell me how much is the potential difference across CC? Potential difference across CC is
So
how
what
much?
is the impedance of CC, sir?
Yes, how much is the impedance of the current coil? I told it just a few.
Very low.
Very low. So
Very low, sir.
ideally 0. So
So
potential.
almost no difference.
Yes.
Almost no difference.
Ideally no
Numerically
difference.
zero.
So ideally no difference. Practically there may be some difference which we will not consider in this course. Okay, so therefore these two are exactly identical. Okay, so instead of drawing this ugly complicated diagram, I could also draw this simplified diagram. Okay, so only about 2 minutes is left, 2 or 1. So I will stop after asking you one question, which is this. Suppose I connect the pressure coil in the opposite direction. Now what will happen? Now what will happen to the wattmeter reading? Anyone?
Negative Same. reading.
Same, sir. Same.
Why same?
Since it takes average, that's why.
Yes, some of you said negative. Actually, it will become negative. Okay, why negative? Because the product of voltage and current is negative for all time, right? Therefore, if you take the average, all quantities are negated, so the average will also get negated. Okay, so therefore it will become negative even if you take the average. So now I can say wattmeter reading is I can say power supplied by load, because the earlier one I said is power consumed by load, so I can say power supplied by load. I may also say minus of power consumed by load, whatever you like. Essentially it will become negative, that's the point.